We want to talk about the curl of a conservative field. We're actually going to prove that the curl of a conservative field is 0. But first we're going to talk a little bit about what a conservative field is. Now, we should understand this by now, but let's just review what we should know and maybe tell you a little bit about what maybe you don't know that you should. Definition of a conservative field is that it's path independent. Meaning if you do the integral of some vector field, of your conservative vector field, like f of xy, or an f of xyz, so you got some vector field, some f of xy or f of xyz field, then the field, if the field's conservative, the integral's path independent, and if the integral's always path independent, the field is conservative. Okay, what do we mean by path independent? It means if we do the integral of f dot dr along any path from A to B, we get the same thing. So in particular, if we've got some closed path that includes the points A and B, if we integrate along this part of the path from A to B, we get the same thing as if we integrate along this part of the path from A to B. Okay, A and B could be any 2 points on a closed path. We would have that property. Okay, well, I want to show that the integral around the entire closed path then has to be 0. And this is really pretty easy to show. The idea simply is, well, if the integral from A to B is the same here as it is here, then the integral from B to A here is being equal and opposite to the integral from A to B, is equal and opposite to the integral from A to B along here. And if we want to go around the path, we go from A to B, then we go from B to A. And if the integral from B to A is a negative of the integral from A to B, independent of what path we take, the whole thing has to be 0. Now let's be a little more specific. Let's let C1 be the clockwise path from A to B along this closed path. So that would be this part. This is the clockwise path. This would be a counterclockwise path. And then we're going to let C2 be the path from B to A. So that if we put C1, A to B clockwise, C2 from B to A, that's still clockwise, we have an integral around the entire path. Now we're going to let C3 be the negative of C2. Remember, C2 goes from B to A, so C3 is the opposite path that goes from A to B. Okay, now the integral of your conservative field or your conservative function dot dr then is what? It's the integral from A to B, that's over C1, okay, plus the integral from B to A, that's over C2. Okay, well, then that's the integral of the conservative function dot dr over C1 minus the integral of this function dot dr over C3. Since C3 is the same as the curve C2, except it goes in the opposite direction. But C1 and C3 both go from A to B, don't they? C1 goes from A to B, and C3 goes from A to B. So that the integral over C1 is equal to the integral over C2. So that when you do the integral over C1 minus the integral over C2, what do you get? You get 0. Many ways to understand that, but that's the case. Now, one application that's related to things that, at least right now, people are doing in physics is gravitational fields. Let's just say that this is the Earth and this is the Moon. Okay? Now, the relative distances are much different. The relative size is actually, Moon is a little smaller than that compared to the Earth, but you get the general idea. Okay, well, we have a gravitational field, the set of gravitational accelerations toward the center of the Earth in the vicinity of the Earth, or let's say, just say outside the surface of the Earth. Okay, at any point, the gravitational acceleration is toward the center. So all these vectors for the Earth point toward the center. Now, if you go twice as far from the center, your gravitational field becomes 1/4 as great. It's an inverse square law. Now, we haven't gone quite twice as far between this point and this point. We've gone further enough that we've gone, some appreciable distance, and the gravitational field is falling off rather rapidly. So that at the points here, 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 and here, we're closer to the surface. At these points further out, we're further away from the surface, the vectors get smaller, but they still point back toward the center. Now, if this is another planet or the moon or whatever, some other gravitational object, we also have a field that points toward this and falls off rapidly with distance. Now, these fields don't stop. I just drew them in close vicinity of both objects. They extend through all space. Another reason, though, I didn't draw them is they get much smaller, so by the time they get out to this region here, both these fields are so small that I couldn't really draw the arrows with a piece of chalk. Okay, so you'd have to imagine much smaller arrows, but then zoom in, the arrows get bigger, and you can see them. Now, if I, at every point, take the arrow that points toward the Earth and the arrow that points toward the Moon, and if we're at equal distances between the Earth and the Moon, the arrow that points to the Moon will be much smaller than the arrow that points toward the Earth. But if I take those two vectors and find the resultant, then I get the resultant gravitational field at this point out here. Okay, now if I do that, then the integral around this path of that gravitational field, which is directly related to the amount of work I would have to do to, say, move a satellite from here around to here, okay, that integral is going to be 0. Because this is a closed path and because gravitational fields are conservative. Now, in the problems, you've hopefully proven that gravitational fields are conservative. It's very easy to prove that. And if you haven't done that, you'll do it in physics. In any case, gravitational fields are conservative, and there's an example of a closed path in a gravitational field around which you would have to do 0 work. Now, a more familiar closed path, because we probably wouldn't want to move a spaceship around this closed path. It would be very complicated. Orbital mechanics is much more complicated than you imagine. In the near vicinity of the Earth, if I did a circular path, and if the Moon wasn't there, or if the Moon's effect was negligible, then again the work around that circular path would be 0. Okay, so I could get around a circular path at, if the circle is centered at the center of the Earth, I get around that kind of for free, don't I? If I have an elliptical path, okay, well, I know that the work I do, if I go from here around to here and back, against the gravitational force is 0. In other words, the change in potential energy is 0 if you understand potential energy. Okay, but that doesn't mean I don't have to have some way to get from here out to here, because that's going to take energy. So I've got to have some kinetic energy here. If I have enough kinetic energy here, it'll be enough to carry me out to here. And then as I come back, I'll regain that kinetic energy. So just a little connection with the physics, and if you don't understand all of that, possibly because you're not taking physics or because you haven't gotten to this, you can kind of ignore it. But that's one really important application of conservative fields, and a little bit about what it might mean. And for anybody else, a little bit of an indication that this is really important. And it's not just for orbits, it's for a lot of things that are right here in front of us on Earth.